My name is Robin Clark, and this is Chapter 4 of the Quick Start Guide series. This guide has been broken down into 5 chapters. This video is on Chapter 4. We will learn the various concepts and terminology specific to continuous modeling. Most simulations run for a specified time. ExtendSim determines the duration of a simulation run based on the values entered in the simulation setup dialog. This dialog can be accessed through the Run menu. The duration is the period from the start time to the end time. In continuous simulations, the duration is divided into intervals or steps of equal length, where the start time is the first step and the end time is the last step. The length of time for each step is known as delta time. As the simulation runs, the simulation time advances from the start time to the end time with a step size based on the delta time. In most cases, a delta time of 1 is adequate. However, for model accuracy, it may be necessary to set a different delta time. Let's look at the delta time, or the number of steps, a little closer. This option, as you can see, is set in the Continuous tab of the Simulation Setup dialog. Delta time literally means change in time. It is defined as the length of the time interval between the present time and one time interval later. When you select a delta time, you are selecting how finely the total simulation time will be sliced up. This sets how frequently the computations will take place. Although 1 is the default setting, delta time can be set to any number. For example, to cause the model to run faster and perform calculations less frequently, delta time could be set to 2 or any other number larger than 1. A delta time less than 1 reduces the step size. This causes calculations to be made more frequently. It results in more steps, and the simulation takes longer to run in real time for the same simulation time. So what should delta time be set to? Here is a rule of thumb to go by to set a reasonable delta time. First, run the simulation with a delta time of 1. Then, run the simulation with a delta time of 0.5 or 1/2 of the original setting. If there is no significant difference between the two, then a delta time of 1 is appropriate. If there is a significant difference, reduce the delta time by half and run the simulation again. Continue reducing delta time until you determine a delta time which results in no significant difference compared to the smaller delta time. The main idea is to use the largest delta time that will give accurate results without slowing down the simulation unnecessarily. ExtendSim requires that either the time per step, which is delta time, or the number of steps be specified. If you enter the number of steps in the dialog, then the delta time will be calculated based on the desired number of steps and the simulation run length. Now let's look at feedback and delays. The practice of connecting an output to an upstream input is called feedback. It is the main factor that causes complex behavior in continuous models. A model with feedback will cause the result of a calculation to be fed back into one of the original variables in the calculation, influencing its own rate of change. Thus, feedback causes repetitive changes to model variables as the simulation runs. The initial output variable ripples throughout the calculations such that the effect loops back and re-affects the initial variable. However, using feedback correctly entails some additional modeling techniques. Since continuous models recalculate at every time step, there will be a delay between when the initial variable first affects the model and when the chain of calculations ultimately and indirectly affects the initial variable. The feedback is delayed by 1 simulation time step. This happens because the output feedback signal has to be calculated before it can be used on the next simulation step. Reducing the delta time of the model will reduce feedback delay and result in a model with more accurate results. Now, let's visit the topic of integration. In Chapter 3, we set the holding tank up to be integrated instead of summed. We did not discuss why at that time. Let's spend a moment and discuss this concept. There are three options to review: summed, integrated with delay, and integrated with no delay. We should use summed when we are adding values and those values do not depend upon time. For example, when we're simply counting things. We would use integration when we are accumulating values when the input is a rate like units per time. The integrated with delay option adds the input value on the next step, not on this step. The integrated with no delay option adds the input value on the current step. The best way to explain the difference is through an illustration. Let's say we have a holding tank with an input of 1,000. Let's say we have a time step of a half of a time unit, not one, but a half of a time unit. So for the summed value, it will simply use the 1,000 as a count. For the integration, we can assume it is a rate of 1,000 per time unit. The values on the chart actually show the resulting holding tank total on each time step. With the holding tank set to summed, it will add 1,000 to the total on every time step. It is not 1,000 per time unit, but 1,000 each and every time it wakes up during the simulation. With the holding tank set to integrated with a delay, then it interprets the 1,000 as a rate per time unit. When the delta time is smaller or larger than 1, then it adjusts the value it adds based on the size of the delta time. In this case, delta time is a half time unit, so it will add 500 to the tank on each time step. It will take one full time unit for the full 1,000 units. Also, notice the result is 0 at time 0. This is the delay concept. The value doesn't actually get added until the following time step. The integrated without delay uses similar logic to the integrated with a delay, except that the addition occurs on that time step instead of the following time step. Now this option should make more sense, but I would recommend you read more about this in the Quick Start Guide as well as the block help. Next, we want to look at the simulation order and how it affects the simulation. For example, does the holding tank wake up before the math block? Or does the math block wake up before the holding tank? Or does it matter? First of all, let's look at this from an individual block's perspective. During a simulation, a block's calculation generally depends upon its inputs. The block will use its inputs to perform its calculations. After the calculation, the block sets its output connectors to the result so that other blocks may use it. Let's look at this from a higher perspective. The order in which the blocks wake up and calculate has an impact and should be understood. In this model, I have numbered the order that the blocks will wake up and calculate. So the holding tank here will wake up after the math block calculates the addition of the lookup table and the random number block. But what if the chart and the holding tank woke up and did their calculation before the math block woke up? Would this affect the results? Yes. Imagine what happens at time 0. If the holding tank woke up and did its calculation before the math, lookup table, and random number block, then at time 0 the holding tank would have a value of 0 instead of what's on its input connector. If the holding tank woke up last, then it would have a non-zero value. Would this ever happen? Of course it wouldn't with the way we have the model set up now. But this topic is about making you aware of the different options you have and its impact. You can see the actual simulation order if you wanted to. Simply go to the Model menu and select Show Simulation Order. The simulation order would be displayed on the blocks as shown here. ExtendSim allows you to control the order in which ExtendSim executes block data for continuous models. We can go to the Simulation Setup dialog to see these options and choose which one the model is to use. The simulation order is set in the Continuous tab of the Simulation Setup dialog. The basic choices we have available are Flow Order, Left to Right, and Custom. This option allows you to choose the order in which ExtendSim executes block data for continuous models. It would be unusual to change the simulation order from the default choice, Flow Order, but you can. Let's look at how each option works. Let's look at Flow Order first, which is the default. There are three basic rules that drive the order when Flow Order is used. The first dictates that blocks which generate inputs to the simulation go first. Notice the lookup table and the random number blocks. Only their outputs are connected to the other blocks, so they would be done first. The second dictates that blocks which are connected to those first blocks go next in the order and direction of their connections. Notice the math block has an order of 3. Notice the holding tank has an order of 4. Let's look at the third rule. I have added 2 data import-export blocks just for this illustration. The third rule dictates that unconnected blocks and bidirectional network blocks are executed in left to right order. The data import-export block on the left had a simulation order of 1, and the one on the right had the simulation order of 7. This is how the flow order logic works. Before moving on to the other simulation orders, I would like to provide a word of caution. The default option of flow order tends to work best. Please use caution before changing the simulation order to something else. Now let's look at the left to right ordering. For this option, ExtendSim looks at the left top corner of each block on the worksheet. The leftmost block gets executed first, and the next leftmost block gets executed second, and so on. Blocks with equal left edges get executed in top to bottom order. Here is where it could get really messy. Let's say that we used named connections for maybe the line chart or holding tank and moved one or both of them somewhere else. Well, as you see here, the line chart is now waking up before the holding tank. This is a great example of why we really have to be careful when we change the simulation order off the flow order. Now, let's look at the custom ordering option. In continuous modeling, there are some situations with multiple feedback loops that do not automatically settle onto the desired flow order solution. This occurs because there are multiple solutions that solve the directed acyclic graph ordering problem, and it is possible for the less desired solution to be picked. I have personally never ran into this problem, but I've heard of it. To solve this ordering problem, first, start out with the order set to flow order and then change the ordering to custom as shown here. Then, you can select a block and open the Set Simulation Order dialog from the Set Simulation Order command. From this dialog, we can enter the desired simulation order for this block. And now we are done with reordering that block. We can simply repeat this process for any other blocks we wish to change the simulation order on. Before moving on, I would like to repeat that the default simulation order is set to flow order. Please be careful if you switch it to a different simulation order. Now let's look at the modeling methods we can use the various blocks in. You can use continuous blocks, such as those from the value library, in both discrete event and discrete rate models. You cannot, however, use discrete event or discrete rate blocks in continuous models. These blocks require the executive block, and that changes the timing of the model to event timing. Now let's look at connectors again, but from a different perspective. You can connect value output connectors to as many input connectors as you want. For example, the output of this equation block is connected to the inputs of several blocks. This is perfectly fine. the output value of the equation block will simply be used by multiple blocks. However, let's look at it from the input connector's perspective. Input connectors can only be connected to a single output connector. For example, the input of the display value block can only be connected to a single output connector. This input connector must get its value from a single source. This concludes this fourth chapter in the Quick Start Guide series. In the next chapter, we will cover various features and capabilities of ExtendSim that you should know about.